Hello, everyone. Thank you so much for taking your time to join today's webinar. As Michelle mentioned, my name is Swati. I'm an applications engineer at MapleSoft, and the topic for today's session is modeling and simulation of hydraulic systems in MapleSim. So before talking a little bit about the hydraulic system, I just want to do a very quick overview if you're someone who's new to MapleSim, just to do a quick overview about the tool itself. So MapleSim can be referred to as a system-level multi-domain modeling environment where you can combine different domains together to build an entire system and simulate the results and observe the dynamics behavior of the model itself. In addition, you also have access to various embedded packages that Maple has to offer to perform analysis on the built model itself. The analysis can be from understanding parameter identification, or something as simple as solving an optimization problem, for example. So we have these custom built-in applications in MapleSim that allows you to do exactly that. And finally, the last part would be the MapleSim connector option, which allows you to export the built and analyzed model in the MapleSim to an FMU or a SQL, which can be placed into a different software. You can also visualize the exported FMU that you have created in the tool by using the MapleSim Insight package as well. All right, so talking about the hydraulics library, I just have a brief snippet of all the components that are associated to our hydraulics library that can be used to build models in MapleSim. So here's a quick snippet of all the components. For example, the fluid properties, which allows you to define the property of the fluid that one wants to model in MapleSim. We have different types of accumulators. We have restrictions, which extends from inertia to resistances to orifices to table-based orifices. We have linear actuators, single and double, different chambers, pipes extending to circular, non-circular, and annulus pipes, and different types of rotary actuators, pumps, and a variety of motors that can be added in, a wide variety of valve palettes that can be added in, and we also have table-based valves. Basically, these table-based valves allows the user to define the pressure and the flow characteristics as data points, or an Excel worksheets that can be added into the component. So essentially, you can bring information from a manufacturer's catalog, for example, and incorporate that as an Excel worksheet into these components that can be simulated in MapleSim. And finally, talking a little bit more about the direction control valves, we have different varieties of DCVs, from 3-way, 4-way to 6-way valves. The configuration are similar to the icons that you see in this section. But let's say that a user wants to create a custom DCV, for example, they will be able to do so by using the generic valve option that we see here. So using this generic valves, you can incorporate the spool position as a function of area of opening, for example, as a data point, or an Excel worksheets that can be incorporated in these components. We will be seeing a very small example of this and how to do this very soon at the end of this presentation. All right, so we spoke about what are the various components that are currently available in MapleSim for building models. Now I'm going to talk about various applications of fluid systems. Of course, this is just a snippet of few examples that I've picked, but MapleSim is not limited to just this, but going over some of the most popular applications here. So under automation, you will be able to create a digital version of a hydromechanical system, mainly for optimizing the control design, for example. Or if you want to analyze some unwanted vibrations in the model, MapleSim would be able to do exactly that. When we're talking about robotics, designing a motion design of a robot, for example, or hydraulic actuation that can be modeled. If you want to identify optimal motor size by observing the speed and the torque characteristics from the system, that can be done later. That characteristics can be compared with online catalog to figure out which motor can be used for the model. When we're talking about aerospace industry, many landing gears and secondary control service actuations use hydraulic systems, and MapleSim can be a tool to do exactly that. And finally, when we're talking about industrial equipments, this snippet that you see here is actually a model of a dual truck mobile sizer that we did with F.L. Schmidt. Basically, this particular model can be referred to as a full-on multi-domain model, which allowed us to perform a series of tasks such as dimensioning of hydraulic components, designing and examining the dynamic stresses in the model, or even load estimation. So these were all the different questions or tasks that were done using this full-fledged multi-domain project. All right, so we spoke about the examples, different applications that can be used. Here is a snippet of one such example. We will be exploring a lot more about this example soon, but this is a snippet of an injection molding machine example that was created in MapleSim. So before creating any systems, the first thing that we want to answer is what it is that you want to solve with our tool. What is the question that you want to answer, or what you want to simulate or capture? Which dynamics do you want to capture with MapleSim? That's the first most thing that we need to answer. With this particular model, we were able to figure out things like what are the pressure drop across various parts in the circuit, how to optimize the control code in the system. And the other question that this particular model was able to answer is analyzing the behavior of unwanted vibrations. If we look at more closely, any model that moves is prone to vibrations. In this particular model, the vibrations were due to the fluid compliances that were occurring in the system. And what we were able to do is efficiently capture that in this virtual machine in MapleSim. And why is that important? Once we have that in place, once we're able to capture the unwanted vibrations, we can look at various test cases to understand how we can rectify these vibrations or improve that vibrations, which is exactly what we did in this case. We were able to improve the vibrations and reduce the vibrations and improve the cycle time in the process of it. And of course, it's not a one-way process. It is, of course, a step-by-step process of understanding what we want to figure out in the model, modeling it, analyzing the system, and going back to the development phase. So here is another example of a multi-domain model. It's a rotary telehandler model that was built with MapleSim. As you can see on the left, this is a multi-domain system with different pieces associated with it. We have the mechanical part for the chassis. We also have a flexible boom design. We also have the hydraulic actuation that you can see on the left. So this particular model allowed us to answer a different set of questions such as checking the stability of the telehandler, for example, or what's the deflection of the telescopic boom, or what are the pressures in the hydraulic cylinders. So these were the things that we were able to answer. And in addition to that, you can actually see that there's an inverse kinematic block that was added to this model. Basically, this IK actor allowed us to actuate the cylinder by ensuring that the platform is leveled, which is very important in terms of the safety aspect of modeling. All right, so we spoke about different examples. Now I want to talk about what is the workflow of modeling fluid systems in MapleSim, and be it any system. We first begin with a concept, or if you already have a CAD in mind, that can be the starting point to begin the model. But of course, if you do not have a CAD, it's always better. It's totally fine. You can start with concept development and build the model with MapleSim, which is the next part. Building the pieces using the library components that are already available. We build the model with all the parts added in, and then analyze the system response. And of course, as I'd mentioned before, this is not a one-way process. It is an iterative process, so you always go back to look at the system response, look to see what, if the analysis is what you're intended for. If not, you go back to modeling the system, go back to the model and tweaking parameters, defining components more clearly. For example, if you want to add in characteristic curves, for example, that can be something that can be put in, and then analyzing the system response again. And of course, if you are in a concept development phase, you can go all the way back to the concept, tweak the concept itself, because this is the fast design iterative process. So within a matter of few clicks, you will be able to do exactly that. And the final phase that I would like to point out is the deployment phase. Deployment phase may mean different to different users. For example, if you are a machine designer, you might want to test this model that you have built in MapleSim in an automation tool for basically kind of testing your control code against this virtual model that you've built. So that will be one phase of deployment, where you will deploy the model as an FMU, which can be placed in a destination tool and tested against the control code. So that way you have a fast, optimized virtual model that is already in the FMU that is incorporated inside. All right, so we spoke about different built-in, we spoke about the workflow of modeling in MapleSim. I also want to talk a little bit more about the built-in applications. So previously I mentioned that with the help of Maple, you will be able to, there are a lot of built-in applications that you can access, and that can be done to analyze your model. And this is basically on the left, a snippet of all the different built-in applications that are readily available for you to perform exactly those analysis. Here is a section of a 1D motion generation app that I have placed here. Basically, this app allows the user to create custom motion profiles that they want to add. Single or multiple motion profiles can be added in a single component and can be generated and connected to other components in MapleSim, which is a good example to point out. Here is another video of a parameter sweep app. So basically, a parameter sweep app allows the user to sweep through a certain range of parameters and obtain the results by overlaying them on top of each other. In this particular app, Maple uses the capability of parallel processing, which allows it to perform many number of simulations within a matter of few seconds. In this case, we're actually doing about 100 simulation or so, with results overlaid on top of each other, which can be later analyzed. So that way you kind of get a better understanding of, if you're not sure of what parameter values to put in, this app can help you do so. We will look at an example soon to which kind of does exactly that. But it is just to point out that these are all the built-in apps which are available for you to use to perform analysis. And of course, you're not just limited to the applications that are already there. Under the template section, we also have a worksheet option, which allows you to attach a Maple worksheet to the model. That way, you get access to all of Maple packages that can be used to perform your own custom app in MapleSim. So you're not just limited to the built-in apps available here. You can do customization and perform different applications in a single worksheet, for example, or if there's a specific unique application that you want to create, Maple worksheets would be the way to go. In this particular example, this is a similar version of a telehandler model that I had shown earlier, where we're using this worksheet to control the motion of the telehandler on insight, which is the right for the visualization. But the idea here is the customization and the ability for a user to create those customizations. Something that I hadn't mentioned, you also have a section called custom component template. Basically, as I mentioned, you're not just limited to the components that are available in the library. With MapleSim, you can get customization. You can do customization, create custom components, and as long as you know the equations associated to the model, you can create a custom component and attach it to other library components and build the model as well. And finally, talking a little bit more about model export. Once you have prepped the model, I will talk a little bit more about this particular component next. But essentially, with the use of FMU generation app, you can export the model that you have built in MapleSim, and that can be placed in other FMI standard tools, which are accepted by many softwares out there. That way, you get the best of both worlds, best of both softwares, and in terms of analysis, for example. All right. So we spoke about a simple introduction about hydraulic system, basic fluid systems in MapleSim. Now we're going to explore a little bit more about the injection molding machine that I had earlier shown. For that, just to save a bit of time, I have a video which I'm going to talk through just to kind of get a better understanding, just saving time and going through what has been done to build that model. So here again, this is a concept of an injection molding machine. It doesn't follow any particular example or anything as of such from online or a particular model. It's just an example that we have created to kind of prove the point of how you can build a hydraulic system in MapleSim. So in here, you can see that all these components associated with this model is been built using our hydraulics library that you see on the left side here. So if talking a little bit more about the model, here we have a variable pump that we have that drives this entire system. The input to this pump is nothing but a signal which demonstrates the speed, which actuates this particular pump. If you look a little bit further up, this pump is connected to this DCV43 floating valve. And you can actually see that it has a particular configuration. It's a three-way DCV flow 3 valve. The input to the valve that you see here is the spool actuation. So based on the spool position that is provided as an input, the configuration of the DCV changes. In addition, you also have a relief valve there, or you can actually call it as a safety valve in this case, where it is used to relieve excess pressure in a circuit. The pressure setting can be placed on the right inside those parameters. Coming back to the DCV, just talking about it, it is a 3 configuration DCV whose configuration value changes from -1 to 1. So based on the input, you can actually see how you can control the valve based on the paths that is provided by the icon that you see. Now, a little bit more further on top, this direction control valve is actually connected to a double acting cylinder, which we're planning to actuate. The parameters for the double acting cylinder are the diameters for both sides, and you also have a mass that is connected to the cylinder as well. So just pause for a quick second. So basically, this mass represents the mass of the moving platen that I have defined in this particular model, which is what is defined here. Now, in addition, there are a few other components here as well. We have 2 relief valves placed on either side of the DCV. And basically, this relief valve maintains a preset pressure differential between the valves that we have between the DCV and the double acting cylinder. And in addition, we also have check valves that are added, which is to basically avoid negative pressure, negative flow going through the system. So this parameter block is where I've defined all the top level parameters associated to the model. So I've just simulated the system right now, and the results are basically the piston displacement and velocity, the cylinder rod, and the cap side pressures as well. So once the simulation is complete, we will be able to see the system results, which is the cap end and the rod end pressures. We have a DCV command that changes from 0 to 1 to -1. We also have a piston displacement and the piston velocity that has been acquired. So this is the first step. Once you have a concept, you build the model using the components in the library. The next part would be basically understanding what can be done after. So in this case, I'm going through the DCV section and I'm dragging in a DCV 43 generic valve. So what this valve, as I mentioned before, allows you to do is allows you to bring customization to the component, where you can actually define the spool path as a function of area of opening. Either you can place it as a data point in this case, or you can add an attachment of an Excel file. And I'm just adding a valve characteristic A, which is already attached as part of this model. So let's quickly open up the valve characteristic A and what it is. So that's under the attachment section. I'm just opening up the Excel, and you can actually see it's nothing but the spool opening, which is from -1 to 1. And all of these are the various paths inside the DCV. The various area of opening for those paths in the DCV are specified. Essentially, you would bring that component from manufacturer's information from the manufacturer's catalog that can be added in. And now I've just included the volumes on both sides of the cylinder, and I've just both sides of the valve, and I've just simulated the results and visualize the system. So this is the next step. It's just a simple example to kind of show you what needs to be done to build build a system from ground up. We build a very simple concept and we develop them as we go further. And of course, in this case, there's just one component that I've used to do exactly that. But in an essential ideal case, you will look at all the components, you will look at the analysis of the model and see what can be done to make it or have the system response closer to what a real system would, how a real system would behave. And that's the process of building models in MapleSim. In the next slide, again, just recapping what has been done, simple concept that has been developed. You model the system with the library, analyze the components, and verify the system response. The next part is basically tuning. The last part is basically the analysis option of, in this case, I've just used a simple analysis of tuning a controller using the built-in apps. But again, this is just an example. You can apply the same concept to different sections, different parts of the model in any model, for example. So here, it's the same version of the model that I'd shown earlier, but all I've done is, so basically I've enclosed all the components inside this plant model. It's a subsystem. When you double click on it, you'll actually see all the components. I've just named that subsystem as plant, and that contains all the components associated that I'd shown earlier. The input to that subsystem is coming from this PID controller that you see here, and you also see some outputs coming out of the controller as well. So here in this PID controller, the gains of the PIDs are all parameterized. The K, TI, and TD are all parameterized. It's a limit PID, which is a limited controller that we've used in this model. If I just quickly pause and look at the other points, the set point that you see here coming out of the subsystem is added in as an input to my controller. The output, the feedback to the controller is nothing but the plant position. So I'm just taking the plant position as my feedback. The input is a given set position that I want my platen to move, which is exactly what I've defined using this particular model. You can also see that there's a parameter block which defines all the top level parameters associated with the model. For example, the areas on both sides of the cylinder, the mass, as well as the gains in the controller are also defined. So I'm just running the model as is and quickly going over the subsystem. So if we go over the subsystem, you can notice that everything is very similar to what I'd shown earlier, the same set of components. You can see the same DCV that I've used with the valve characteristic A that is defined. I think the one addition that has been added in is the new additional motion, which is the set motion for that I want the PID controller to follow, or this model to follow. I've also added a friction for the piston to slide in, which is a simple component that I've used. And that is the sensor which senses the plant position, which acts as a feedback to the system. Everything else is the same. We have different sensors that measures characteristics of the system as well. So let's look at the system response. And when we look at the set and the plant position, we're just overlapping the results on top of each other. And you can actually see that there's a bit of an overshoots on both sides, meaning the controller is not doing a great job in this case. So for this, solving this particular use case, what I'm going to do is I'm going to go to the apps and templates folder, and I'm going to use a parameter sweep app. So a parameter sweep app, as I mentioned, you load the model. So all the information in the model gets loaded in. And all I'm doing in the next process is defining a range for different parameters that I want to vary. In this case, I'm just varying my K, TI, and TD, which is the controller gain that I want to change. And I'm defining the data points and measuring the outputs. So as soon as I hit run parameter sweep, and what happens is, in this case, I think 100 simulations are running in the background. And once the simulation is complete, we should be able to see an envelope of results that are overlaying on top of each other. And what this allows us to do is it allows us to kind of perform some analysis, look at which parameter values will be the most appropriate ones to use for the model. And then we can incorporate that back in the model itself. So the simulation is complete. And as I go further down, this is just an envelope of the model. But if I uncheck the envelope, you can actually see the overlay of all the results on top of each other. And all I'm doing is using the fix option to fix and change parameter values and see which one would be the best option to sweep. And that's exactly what I've got. And so based on the parameters, I'm just changing the values here, simulating the results. And once the results are simulated, now we can see the set and the actual position overlaying on top of each other with the model with a good margin. So this is an idea, as I mentioned before, an idea of one such analysis that can be performed with MapleSim. Again, there are many more that you can do, and you can use the same application that we have shown here to perform different analysis as well. As I'd mentioned, under the apps and templates folder, you have much more applications that can be done, but this is just one such model and one such use case to do that. So that kind of ends the presentation for today. It's just a simple snippet of showing what other things that you can do in the next process. As I'd mentioned, parameter sweep is one option. The other option is just a worksheet, which I'd mentioned earlier. You can use Maple worksheets to do your own custom analysis rather than using the built-in ones. I think the advantage is you have much more control over, let's say you want to add different analysis on the same worksheet. You can do that by attaching this worksheet and doing exactly that.